So this is the example we'll be working on here, the parallel example. And with the parallel example, remember, voltage is all the same across all these components. They share the same two terminals of the source. And so we're going to have a in phase value for when it comes to E source equals VR equals VC. And all of those voltages will be in phase. But we are going to have a current triangle that is resulting from this to prove Kirchhoff's current law, and we would have IR, IC as a leading value as a plus J component. Remember, IL was minus J, and I total here. Now, in the current triangle, this is going to represent theta because we know that we have here is where we have our E source. It's your source voltage and your resistive current are always going to be in phase. This obviously equals VR equals VC. So in terms of determining impedance as well here, we can use I total to determine impedance. So not only product over sum, but I total could be used to determine, I total can be used to determine the impedance as Z total equals E source divided by I total. So keep that all in mind as we go through solving these values and okay, so now we're looking at the parallel example and using the same values we did in series. So we have our 10 ohm resistor in branch 1 and our branch 2 opposition of our 8.04 ohms as the reactance value from that 330 microfarad capacitor. So in going forward with a parallel example, what's a common approach is just to go directly to current, and I'll show you how through current you can really come up with everything you're looking for in parallel. So don't forget this applied voltage is 120 volts, 60 hertz. So we can start by determining our IR value here. IR is going to equal 120 volts at 0 degrees divided by 10 ohms at 0 degrees to give us 12 amps at 0 degrees. So there you go. We've got our branch 1 current already. Now we're looking at our IC value. IC is equal to 120 volts at 0 degrees divided by our XC value of 8.03 ohms at an angle of minus 90 degrees. That's going to give us a current that will be 120 divided by 8.04 to give us 14.9 amps at an angle of plus 90 degrees. Now, that's a capacitive branch. So notice how ICE applies. We've got the applied voltage and the current, 14.9 amps, is leading. This is leading that voltage. That's leading E source. So this is all lining up the way it should. And if we look at our current triangle to prove Kirchhoff's current law, what are we going to have? We're going to have IR of 12 amps. We're going to have a leading current here. So the leading current, IC, is going to be 14.9 amps. And the total current will be here, right? I total. So the I total value can be expressed as 12 amps plus J 14.9 amps, or as a polar value, we've got 12 plus J 14.9, and we convert that to polar, and we've got 19.1 amps at an angle of 51 degrees. So that means the angle here is 51 degrees, and that's going to be our angle theta. And again, how do we know from a current triangle that that's actually the angle of the phase angle of our circuit? Well, we need to know where to find E source in this current triangle, because we know that the angle between the applied voltage and the total current is the circuit phase angle. Well, remember, our E value, E source in parallel, is equal to VR is equal to VC. So we have all in phase voltage. There's no way any one of those branches could have a voltage at a maximum value while the other was at a minimum. It's a parallel connection. So we know that we have an in-source voltage for all of the branches and the source, and that is definitely VR and IR are going to be in phase. So as a result, we can see with source as the reference in the current triangle, we find I total up here, indicating the circuit phase angle for this diagram. Okay, now lastly, guys, we could use product over sum in this example to determine the total impedance, but we can also come up with total impedance, Z total, as equal to E source at 0 degrees divided by I total at angle theta to give us our result. So we had 120 volts at 0 degrees divided by 19 amps at 51 degrees, which is going to be 120 divided by 19, 6.3, let's say, 6.3 ohms at an angle of minus 51 degrees. So this is the value of polar impedance, Z total. We could come up with a rectangular value by changing our representation to rectangular. Just a sec here, guys. 120 divided by 6.3. Okay, coming back to this then, we've got our value in polar. We're going to represent it now as our rectangular value, so we're going to have 3.96 ohms, and then our imaginary value is plus minus J 4.9 ohms. So if we were to actually look at representing the impedance triangle from this parallel circuit, we'll be looking at a value of R equal to 3.96 ohms and a value of XC equal to 4.9 ohms as a minus J value. And the total impedance is here of 6.3 ohms, Z total, and this angle is going to be 51 degrees. Now, what are we really saying when we show an impedance triangle from a parallel circuit? What we're actually demonstrating is we're saying what is the equivalent series value of that parallel impedance. So what we're saying is, a sec here. just like we're looking at a parallel value of 10 ohms in parallel with 10 ohms as a resistance, giving us our equivalent value of 5 ohms. The 5 ohm value is the equivalent series resistance, right? R equivalent is equal to 5 ohms. It's the same way in which we are looking at a parallel arrangement of R and C and saying what is its Z equivalent? What's its equivalent impedance if it was a series arrangement? Well, that's represented by this current triangle here, or sorry, this impedance triangle, and it's saying its equivalent value as if it was series would be a 3.96 ohm resistor in series with a capacitor that has an XC value of 4.9 ohms. The Z equivalent value is one that's being represented as its series equivalent right here.
Okay, so here we are with our parallel example, the first one out of the table you were given to practice, and the same values as we use for series. We've got them connected in parallel now. We can see that we've got our AC ammeters to give us our RMS values of current, and our total current here is our 19.2 amps measured by XMM1. XMM2 is our resistive branch, of which is determined by 120 volts divided by 10 ohms. We've got our 12 amps that would be in phase with our applied voltage here being a resistor. Over here is where we have our capacitive branch, and this is the current that flows as a result of the reactance of this 330 microfarad. And that's going to be a leading current. So that current is going to be leading the applied voltage, as we know, because of the ICE relationship. We are going to have leading current, and that's 14.9 amps. So we've confirmed the branch currents, and we would have to add them in a current triangle where the hypotenuse would be this value. You can certainly see if you just add these up directly, you would get the wrong result. You have to go about a process of rectangular to polar conversion to give this value, and figure out the angle, or use a current triangle to get the result. So this is what we've got for our current values. I'll set up the oscilloscope and we'll come back here in a second. Okay, so I've set up the oscilloscope here. And if you take a closer look, notice how I've got that 1 micro ohm sampling resistor in here. And I talked about that before in terms of an oscilloscope being used to represent current in a circuit. Something like a really low value of resistance like we have here can be put in series to act like an ammeter, such that the voltage across it as a resistive component will be representing the phase of the current through it. So we can use that to look at the total current here because of where we put that sampling resistor, and we'll use that to determine the circuit phase angle. So if I just start up this oscilloscope display here, what it means is we can take a look at the time displacement like we've been used to in order to determine the actual phase shift. So I'm just going to pause that there, and we know that we've got a leading current here, right? We can see the value leading the voltage, and we can see the red is the current and the blue is the voltage. So I'm just going to take these markers and align them with a zero, as close as we can to a 0 point, and then we're going to do the same thing with the voltage. So I'm looking at channel A now and time 2. That's going to be as close as we get to that. Okay, so if we look at the results here I have from lining up those markers using the oscilloscope, we can see we have a T2 minus T1 here of 2.37 milliseconds. And if you run that through your calculator as 2.37 divided by 16.67 to give you a fraction to multiply by 360 degrees, you get 51.1 degrees. So we've demonstrated the circuit phase angle through the use of a sampling resistor here.